New Higgs boson discoveries that could change physics forever. More than a decade ago, the discovery of the Higgs boson rocked the world of physics, becoming one of the most important advances in our quest to understand the universe. This elusive particle has been the subject of rigorous research, continually revealing the mysteries of the structure of the universe. Now, groundbreaking discoveries made by scientists at the Max Planck Institute and the Large Hadron Collider, LHC, have pushed the boundaries of our knowledge even further. Using advanced data collection techniques such as precision particle detectors and powerful machine learning algorithms, researchers have been able to analyze billions of particle collisions with high precision. The ATLAS and CMS detectors have played an important role in capturing rare Higgs boson interactions, including its possible decay into charmed quarks. These advances have been made possible by significant technological improvements in detector technology and data processing, opening new horizons for the study of the structure of matter. These results not only confirm long-standing theories, but also hint at the possibility of physics beyond the standard model. In particular, they may shed light on alternative theories such as supersymmetry SUSY, which predicts the existence of new, heavier partners of known particles, and the extra dimensions hypothesis proposed within string theory. If new experiments show deviations from the predictions of the standard model, this could indicate the presence of unknown interactions or particles, such as axions or bosons associated with dark matter. In this piece, we will delve into what these discoveries mean, why they are so important, and how they will affect the future of particle physics. Recent discoveries in Higgs boson research. The Higgs boson has always been a cornerstone of the standard model of particle physics, explaining how particles acquire mass. Recent research has provided unprecedented information about its behavior and interactions, further strengthening our understanding of this fundamental particle. One of the most significant observations has been the interaction of the Higgs boson with W bosons. The data, analyzed at a statistical confidence level of 5.3 sigma equivalent to flipping a coin that falls heads more than 1,000,000 times in a row, confirmed that the Higgs boson decays into bottom quarks in the presence of W bosons. This not only confirms predictions made decades ago, but also becomes an important benchmark for future studies of particle interactions. Similarly, scientists have studied the interaction of the Higgs boson with Z bosons in detail. At a confidence level of 4.9 sigma, a similar decay to lower quarks was observed, further strengthening theoretical models of particle physics. Although these observations are slightly less statistically significant than the interaction with W bosons, they still confirm the key role of the Higgs boson in the standard model. An even more challenging task has been to study the possible decay of the Higgs boson into charmed quarks, a process that occurs much less frequently. So far, no direct evidence has been obtained, but scientists have established upper bounds on the probability of such events, which is important for further refining theoretical models and developing more sensitive experiments. Even the absence of detections provides valuable information, allowing us to adjust the direction of future research. These discoveries not only confirm the key role of the Higgs boson in elementary particle physics, but also deepen our understanding of the mechanism of mass formation. The Higgs boson is associated with the so-called Higgs field, an all-pervasive energy field that plays a crucial role in the process. Imagine particles moving through an invisible network, gaining mass as they interact with its threads. This is the Higgs mechanism that scientists are striving to fully understand. Implications for the Standard Model and beyond. While new discoveries confirm the fundamental principles of the Standard Model, they also open the door to the search for new physics, forcing scientists to rethink existing theories. The Standard Model, despite its incredible success, has several limitations. For example, it does not explain the existence of dark matter, which makes up 27% of the universe, or dark energy, which is responsible for its accelerated expansion. The confirmed interactions of the Higgs boson with W and Z bosons reinforce the predictions of the Standard Model, but any deviations from these results could indicate the presence of new particles or forces. Anomalies in decay patterns, for example, could point to undiscovered dimensions or interactions that would radically alter our understanding of the universe. One of the most exciting challenges remains the search for the Higgs boson decaying into charm quarks. If this process is observed, it would provide crucial insights into how the Higgs interacts with second-generation quarks, potentially expanding the Standard Model. This knowledge could help physicists address fundamental mysteries, such as the matter-antimatter asymmetry, which explains why our universe is dominated by matter rather than antimatter. Furthermore, studying the Higgs boson could be the key to understanding the early stages of the universe's evolution. The Higgs field is believed to have played a critical role in cosmic inflation, the rapid expansion of the universe in the first fractions of a second, with the Big Bang. Its interaction with fundamental particles may have influenced mass distribution and the formation of galaxies. Alternative hypotheses, such as the interaction of the Higgs field with hypothetical scalar particles or dark matter, could shed light on the nature of these processes. Some theorists suggest that fluctuations in the Higgs field in the early universe might have led to different scenarios of cosmic evolution, including the possibility of multiple universes with varying fundamental constants. The future of particle physics research. The recent discoveries are just the beginning. The High Luminosity Large Hadron Collider, LHC, a revolutionary upgrade to the LHC, promises to elevate Higgs boson research to an unprecedented level. A significant increase in collision rates will generate vast amounts of data, enabling the study of rare processes and interactions with unmatched precision. One of the primary goals of the whole LHC is to revisit elusive processes, such as the Higgs boson decaying into charm quarks. With its enhanced capabilities, this accelerator will be able to detect rare events that were previously beyond our reach. Success in this endeavor could fundamentally change our understanding of particle interactions and lead to breakthroughs in mass generation. However, Higgs boson studies are not the only focus. The collider will also be used to search for deviations from Standard Model predictions. These anomalies could reveal particles that make up dark matter or even uncover entirely new fundamental forces. For instance, if unexpected decay channels are observed, it could signal the existence of previously unknown dimensions or interactions that challenge current theories. Technological advancements will play a crucial role in these explorations. Artificial intelligence and machine learning are already being integrated into data analysis, helping researchers process vast amounts of information and identify hidden patterns. These technologies are used for automatic classification of particle collisions in LHC experiments, allowing for the rapid detection of rare events, such as unconventional Higgs boson decays. Additionally, machine learning is applied in simulating particle behavior, improving predictive accuracy, and aiding in the development of new methods for detecting unknown particles. These tools are indispensable for identifying rare phenomena that might otherwise go unnoticed. Beyond colliders, the future of particle physics. The future of particle physics extends beyond accelerators. In addition to the LHC, other groundbreaking experiments will significantly contribute to our understanding of fundamental physics. Cosmic ray detectors, such as the Pierre Auger Observatory, study ultra-high energy cosmic particles originating from deep space. These observations help scientists understand the origins of cosmic rays and explore new physical processes that might not be accessible through traditional accelerators. Quantum simulators. Built using cold atoms and entangled quantum states, allow researchers to model complex particle interactions under controlled conditions. These simulations can provide insights into fundamental quantum processes that occurred in the early universe. Neutrino observatories, such as IceCube in Antarctica, detect rare neutrino interactions, offering valuable data on dark matter and the fundamental properties of subatomic particles. Next-generation projects, such as advanced neutrino detectors and gravitational wave observatories, will complement Higgs boson research by providing a more complete picture of the universe, from its smallest particles to its largest structures. Looking ahead, it is clear that the Higgs boson is just the tip of the iceberg. Each experiment, observation, and discovery brings us closer to answering the fundamental questions. What is the universe made of? How did it begin? And what lies beyond the limits of our current understanding?
GPS, or Global Positioning System, has become an integral part of our lives. It helps us find our way, track the location of devices, provides accurate time, and much more. But have you ever wondered exactly how GPS works? How a small device in your pocket is able to get accurate data about your location to within a few meters? Let's take a look at this fascinating and complex process. The history of GPS, from military development to mass use. GPS was developed in the 1970s by the U.S. Department of Defense. Initially, it was used exclusively for military purposes such as navigating submarines and airplanes. However, in the 1980s, access to GPS was opened up for civilian use, kickstarting the development of navigation technology. Today, GPS is used everywhere, in smartphones, cars, aviation, marine transportation, agriculture, and even sports trackers. The system has become a mainstay for many industries due to its versatility and accuracy. The basics of GPS, satellites, signals, and receivers. GPS is a network of 31 active satellites that orbit the Earth at an altitude of about 20,000 kilometers. Each satellite transmits radio signals containing information about its location and time. Your GPS receiver, whether it's a smartphone or the navigator in your car, receives these signals and uses them to calculate your location. The way GPS works is based on a method called triangulation. To determine your location, the receiver must receive signals from at least 4 satellites. Why 4? To determine the distance to the satellite. The receiver measures how long it took for the signal to reach the device. Knowing the speed of light, since the signal travels at the speed of light, the device can calculate the distance to the satellite. Determining position in 3-dimensional space. A signal from one satellite indicates that you are somewhere on the surface of a sphere with a radius equal to the distance to the satellite. Signals from 2 satellites create the intersection of 2 spheres. A 3rd satellite allows you to determine your exact location. The 4th satellite is used for time correction because the built-in clocks of GPS receivers are less accurate than the atomic clocks on the satellites. GPS accuracy. What does it depend on? GPS accuracy depends on several factors. Errors in time measurement. The main component of GPS is accurate time. Satellites have atomic clocks that have incredibly small errors, but receivers use quartz clocks that are less accurate. Therefore, adjustments to the signals are required. Ionospheric and tropospheric interference. Atmospheric layers distort the signal, which can introduce small errors into the calculation. Satellite location. If the satellites are close together from the observer's point of view, it degrades the accuracy of the calculation. This effect is called geometric blurring of precision, GDOP. Local obstructions. Tall buildings, mountains, or trees can reflect signals, creating what is known as multipath interference. This is especially true in urban environments. Modern technologies such as augmentation systems, WAAS, EGNOS, and data correction, DGPS, help minimize these errors. GPS applications, from navigation to scientific research. In car navigation, the best known application of GPS is navigation in automobiles. Modern systems take into account traffic jams, plot optimal routes, and help avoid accidents. Aviation and maritime transportation, GPS plays a critical role in flight and shipping safety. GPS systems allow airplanes and ships to navigate in low visibility conditions. Agriculture. In smart agriculture, GPS is used for precision fertilizer application, seeding, and even controlling unmanned tractors. Rescue operations. GPS helps find missing people, track the movement of rescue teams, and evacuate people from dangerous areas. Science and research. Surveyors use GPS to create accurate maps, and scientists study tectonic movements using satellite navigation data. How does GPS tell time? One of the unique functions of GPS is to provide accurate time. The atomic clocks on the satellites are synchronized to the International Time UTC. Each satellite transmits a signal containing a timestamp. This time is used to calculate the signal delay and determine the distance to the satellite. Accurate time synchronization is also important for the operation of financial systems, telecommunications networks, and power plants. Alternatives to GPS, GLONASS, Galileo, Beidou. Although GPS is the best-known navigation system, there are others. GLONASS, Russia. An analog of GPS, especially useful in northern latitudes. Galileo EU, a civilian system that provides improved accuracy. Beidou, China. Actively developing and already competing with GPS. Many modern devices support multi-innovation systems, which improves accuracy and reliability. The future of GPS. New technologies and opportunities. GPS technology is constantly improving. The future holds. Increased accuracy down to a few centimeters due to new satellites and technologies. Integration with augmented reality systems. The use of GPS in autonomous driving systems. The development of the Internet of Things, where millions of devices will interact using GPS. GPS is one of the greatest achievements of modern science and technology. It allows us to feel confident in any corner of the world, whether it is a dense forest, megalopolis, or desert. The principles of GPS are complex at first glance, but it is the elegance of scientific ideas that has changed our lives. Now, knowing the basics of GPS, you can appreciate this technology not only as a handy tool, but also as an example of what human engineering is capable of. If you like this story about how GPS works, don't forget to subscribe to the channel. Here you will find even more interesting, informative, and entertaining materials that make the complex simple and understandable. Support the channel with a like, subscribe, and click on the bell not to miss new videos. Thank you for your support.
Before the first glimpse. Close your eyes. Imagine a time before stars, before galaxies, before atoms as we know them. A time when the universe was nothing but a seething, glowing soup of energy and particles. Then, in an instant, the fog lifted. Light was born, and that light never stopped traveling. In 1965, two scientists stumbled upon it by accident, the afterglow of the Big Bang. It was the faintest whisper of the beginning of time, and it changed everything. This is the story of that light, the cosmic microwave background, and how one image transformed our understanding of the entire universe. The echo of creation. The cosmic microwave background CMB is the oldest light in the universe, a fossil imprint from just 380,000 years after the Big Bang. Before this moment, the universe was opaque. Photons, particles of light, couldn't travel freely. They were constantly bouncing off electrons and protons in a hot plasma. But as the universe expanded, it cooled. Electrons combined with protons to form neutral hydrogen atoms. And finally, light broke free. That moment, called recombination, allowed light to travel across the cosmos. And some of that light is still reaching us today. The accidental discovery. In 1965, Arno Penzias and Robert Wilson were using a large radio antenna in New Jersey to study the Milky Way. But they kept picking up a strange, persistent noise. It came from every direction. It was always there, and they couldn't get rid of it. They tried everything, cleaned the antenna, checked their equipment, even removed pigeon droppings. But the noise remained. Unbeknownst to them, a group of physicists at Princeton had just predicted what this noise might be: the afterglow of the Big Bang. When the two groups connected, history was made. Penzias and Wilson had found the CMB, the first light of the universe. Mapping the oldest light. While the discovery was groundbreaking, the CMB looked boring at first: a uniform background, the same in every direction. But scientists knew there must be tiny fluctuations, small temperature differences, that seeded all the structure in the universe. Galaxies, clusters, you and me. In 1990, NASA launched the COBE satellite, which detected these variations. Then came WMAP in 2001, and finally Planck in 2009. Each mission painted a more detailed picture of the infant universe, a snapshot of the cosmos at 0.003% of its current age. Reading the code of the cosmos. The fluctuations in the CMB tell us everything. The age of the universe, 13.8 billion years. Its composition, 5% matter, 27% dark matter, 68% dark energy. Its shape, almost perfectly flat. The seeds of structure, quantum fluctuations from the earliest moments. By analyzing the pattern of hot and cold spots, scientists have built the standard model of cosmology, the most successful description of our universe to date. The CMB acts like a cosmic DNA. It holds the genetic blueprint of everything that followed. The sound of the universe. Believe it or not, the early universe rang like a bell. As photons pushed against gravity, they created pressure waves, acoustic oscillations in the primordial plasma. These ripples left imprints on the CMB, much like the overtones in a musical chord. These patterns tell us about the density and structure of the early universe. They help us measure cosmic distances and understand dark energy. In a way, the CMB isn't just light. It's sound frozen in time. A message from the beginning. The photons we detect in the CMB have been traveling through space for nearly 14 billion years. Along the way, they passed galaxies, clusters, and massive objects, their paths warped by gravity. This bending of light, gravitational lensing, leaves fingerprints on the CMB, giving us a map of the dark matter web that connects everything. It's as if the universe sent us a message, not just about its birth, but about everything that's happened since. Beyond the observable. The CMB marks the edge of the observable universe. We can't see anything farther because light from beyond hasn't had time to reach us, but that doesn't mean the universe ends there. It might go on forever, or it might curve back on itself, or be one of many. The CMB is our horizon, the limit of what we can know. But it also hints that reality is far bigger, stranger, and more beautiful than we can imagine. The image that changed everything. In 2013, the European Space Agency released the most detailed image ever made of the early universe, Planck's CMB map. It showed, in exquisite detail, a baby picture of everything, a snapshot from before stars, before galaxies, before life. And yet, within that image were the seeds of it all. It's hard to overstate how profound this image is. It connects us to the beginning, confirms our theories, and reveals mysteries still unsolved. The universe spoke, and we listened. The light that never faded. The cosmic microwave background is not just light. It's a message, a memory, a moment frozen in time. It reminds us that we live in a universe that had a beginning, that we are made from its echoes, that everything we see was once contained in a whisper of fire and light. And that light never stopped shining. Subscribe for more cosmic journeys. The universe is just getting started. What if I told you that we are all along with the Milky Way, our entire local group of galaxies, and even entire superclusters being sucked in by something huge, invisible, and unexplained? Astronomers call it the Great Gravitational Anomaly, or the Great Attractor. It attracts billions of stars and galaxies, but we know almost nothing about it. In this video, we'll explore what the Great Attractor is and where it is located, why it doesn't fit into current cosmological models, how it affects our galaxy and all nearby clusters. Could it be part of an even more gigantic structure that controls the motion of the universe? Fasten your seatbelts, we are in for a grand journey into the depths of space. The Great Attractor, the gravitational giant. When astronomers were studying the motion of galaxies around us, they noticed a strange phenomenon. The entire local group of galaxies, including the Milky Way, Andromeda, and thousands of other galaxies, are moving in the same direction at a speed of about 600 kilometers per second. Something invisible but incredibly massive, like a magnet, is pulling them to the same point. This phenomenon was first discovered in the 1970s, and by 1986 scientists had given it a name, the Great Attractor. It is located about 250 million light-years from Earth, in the direction of the constellations Centauri and Hydra. But here's the problem. When scientists pointed their telescopes to this region, they saw nothing that could explain such a powerful gravitational pull. Why can't we see it? The mystery of the shelter zone. The main reason why we can't see the Great Attractor has to do with the fact that it is behind dense clouds of gas and dust in the plane of our galaxy. This region is called the hiding zone because conventional optical telescopes are simply unable to penetrate through the thickness of interstellar matter. However, the use of infrared and X-ray observations has helped reveal that this region does indeed contain a huge cluster of galaxies. But even that doesn't fully explain such powerful gravity. What then? Dark matter and the invisible mass hypothesis. Some astronomers believe that the Great Attractor is actually part of a giant cluster of dark matter. Dark matter is a mysterious substance that makes up about 85% of all mass in the universe, but does not emit light or interact with ordinary matter, except gravitationally. Studies have shown that the Great Attractor may be part of an even larger structure, the Laniakea superunit. This is a colossal gravitational network of about 100,000 galaxies. But the most interesting thing is, if Laniakea is a huge stream of galaxies, what is at the center of this system? Is there a possible scenario in which the Great Attractor is connected to even more gigantic structures? Superscale structures. What is the Great Universe Web hiding? When we look at the universe at the largest scales, we see that it is not organized chaotically, but as a vast cosmic web. Galaxies and clusters are connected by long strands of dark matter filaments that form giant voids in colossal walls. Examples of such structures: Sloan's Great Wall, spanning 1.4 billion light-years. The Hercules Corona Borealis supergroup, 10 billion light-years. Could the Great Attractor be part of one of these superstructures? Or perhaps it is a bridge connecting several supercopters. The Great Attractor and the fate of our galaxy. We know that in 4.5 billion years, the Milky Way and Andromeda will merge into one huge galaxy. However, in the much longer term, an even grander event awaits us: to collapse into the Great Attractor. So far, this process has taken billions of years, but it is inevitable. If the gravity of the attractor is so great, it can warp the trajectories of entire galaxy clusters. Could we be on the verge of a giant collapse someday? Relation to alternative theories of gravity. Some physicists suggest that the Great Attractor may be a testing ground for alternative theories of gravity. For example, modified Newtonian dynamics (MOND) explains anomalies in the motion of galaxies without dark matter. The FR theory of gravity proposes a generalized form of the general theory of relativity. Fifth dimension hypothesis considers the possibility of additional dimensions influencing gravitational forces. If the Great Attractor does represent a deviation from standard models, it could fundamentally change the understanding of the physics of the universe. Is the Great Attractor the key to understanding the universe? We stand on the threshold of one of the greatest discoveries in astronomy. The Great Attractor is not just an anomaly, it is a crucial structure that can shed light on the true nature of dark matter, gravitational coupling on the scale of the mega-universe, the future of the Milky Way, and all of Laniakea, the ultimate fate of the universe. Perhaps in the coming decades, new telescopes like the James Webb and Vera Rubin Observatory will help us unlock the final mystery of the Great Attractor. But for now, it remains one of the greatest cosmic phenomena waiting to be explained. Interesting facts about the Great Attractor. 1. The Great Attractor is not a point, but a giant region. Contrary to its name, the Great Attractor is not a single massive structure, but a huge region filled with thousands of galaxies and possibly a dark matter superscope. 2. The Milky Way and all neighboring galaxies are moving toward the attractor. Our galaxies are flying towards it at 600 kilometers per second. That's about 2.2 million kilometers per hour. 3. Shelter zone interferes with observations. The attractor is hidden by dense clouds of interstellar gas and dust, making it impossible for optical telescopes to see it. Only X-ray and infrared instruments allow it to be studied. 4. The Great Attractor is part of the vast Laniakea network. It is just the central gravitational point in the Laniakea superscope, which includes 100,000 galaxies, including our own. 5. Its mass is comparable to millions of Milky Ways. The attractor contains trillions of times more mass than our galaxy. 6. The future of our galaxy is tied to the Great Attractor. Perhaps billions of years from now, the Milky Way will be an inseparable part of the attractor, merging with other galaxies. 7. Could the attractor be a window to another part of the universe? Some scientists speculate that it could be a gravitational anomaly associated with hypothetical multidimensional structures. 8. It was discovered by accident. Research into the motion of galaxies in the 1970s led to the discovery of this mysterious force, which had not previously been suspected. 9. Dark matter plays a key role. Much of the attractor's mass may not be made up of ordinary matter, but of dark matter, making it even more mysterious. We are all travelers on a giant cosmic stream. All galaxies, including our own, are moving along the gravitational threads of the universe, and the Great Attractor is one of the main centers of this movement. If you enjoyed this journey into the depths of space, don't forget to subscribe and like. Space is waiting for us, and there are still so many mysteries in it.